All right, good morning. Today we're going to study the analysis of multi-cells thin structures. So the first thing we need to do is to recall one equation from probability structures 1, which is recalling the shear flow distribution in an idealized thin structure So what was the expression? The expression is shear flow along the structure is given by minus Vx I x x minus Vy I x y divided by I x x I y minus I square xy and here we should have two terms, 0 to the length of t x ds. So this is the effect of the panels plus r equal to 1 to n of b sub r x sub r, and this is the effect of the booms or the stringer or the fans basically. So this expression is for any type of beam, so unsymmetric, so we need another term. Let's say this will be the effect of the shear due to the bending in that direction, then we need the one bending in that direction. So we go to the next line. So the first term over here would be Vy Iyy. So this is the term on the effect of Vx Vy Iyy minus Vx Ixy, right, divided by the same term as over here, Ixx Iyy minus Ixy square. So now we're gonna have is basically a very similar term to this one, t, but instead of x we have y ds, and here we're gonna have r to 1 to n b sub r y sub r, and now plus q sub naught. So this is for closed structures. Okay. So the above equation is valid for closed sections for which q sub naught will be equal to 0, this term over here, and open sections do not different than 0. So T on the above equation is the skin / panel thickness. B sub R is the equivalent boom area. As I mentioned before, this is representing flanges, stiffeners, and so on, so on. Okay, so the Vx, Vy, these are shear forces, and all the I's would be moments of inertia. Alright, so that's the basic equation over here. So, so far you must be proficient at solving the, let's say, the one cell problem. So first one would be, let's say, the open sections, where you study this type of problems over here. Okay, the little circles would be the boom areas, all right? So this is an open section. Okay, and so actually this is all right, so any type of open sections, and you will solve these problems over here. This is the two typical problems to solve, the C sections and the L sections. So what happened here, you don't need to make a cut, because here you can start from one end. Let's say this would be S, or this would be S. So you can start from one end, and here Q will be 0, so you can start making the calculation. So you should have done this and calculate the shear distribution on each one of these flanges or stiffeners, and as well you should have done the study for one single cell, let's say, subjected to some type of shear force. So in these cases here was always some type of shear force, let's say going this way, you just do the Y, or okay, or you could do this one here, let's say this one, and you calculate the shear distribution. All right, so now we try, and this is open, this is closed. So what happened on this one, you need to make a cut somewhere so that you could start doing the shear distribution, okay, the calculations. So now the goal for this class is more calculate the same thing, but let's say for a structure that will have multiple cells. So let's say this type of structure over here. Okay? Alright, so let's go through the general procedure. General procedure. So let's see. One, So we need to start from one location. That means that we need to make a cut, all right? So we can start from 0. So make a cut on each cell to have a starting value to evaluate QS. So basically, we need to evaluate QS using this expression here. Alright, so in most cases it will mean at one point where Q will be equal to 0. Two, starting, okay, so I'm going to repeat here, starting from cut, you evaluate the shear flows, alright, the third step is assume, and I will do a little sketch over here, assume an unknown constant shear flow due to torsion in each cell so the condition is that we'll make the twist of each cell the same. So let me do a quick figure over here. So let's say we have a 2 cells thin structure, so this way. So you will assume due to torsion, Q1, Q2 due to torsion, and this might happen because of what? Because maybe your load, okay, will be applied, let's say over here. So this will create just shear about this, but also will create torsion, okay? So these two moments need to counter-react the moment created by Vy, okay, by creating, if you want, a moment going in the opposite direction, all right? So the way to calculate this is that now the angle of twist needs to be the same. So what does that mean? That d theta, say this, it doesn't matter the current system we're using, so one, or the first cell, which would be this one here, should be equal to the angle of twist of the second cell. And I use basically z because if this is x and y, it will be, torsion will be about the third axis that will be coming in or out. All right. So this is the condition over here. Okay. Where d theta dz will be given by the expression 1 over to a integral of q over gt ds. And this means that you need to go across the cell, so all across this. Alright, so and step 4, would be to, okay, so now one additional equation, so additional equation for this case, but you have more than 2 would be equations, are obtained by equating the moment created by the external force, what we just say Vy, to the moment created by the internal shear forces. So basically over here is not only Q1, Q2, because you also have shear forces going along each one of the members, but if you want all those shear forces that will be internal need to counter-react whatever effect this force is, whatever moment this force is creating, in addition to the just force on the y direction. Alright, so I think the best way to understand this is to do an example. Okay? So just gives you the heads up, these problems generally are a little bit long. They're not difficult, but they're a little bit long. Okay. Alright, so the example we're doing is example Alright, so basically the same structure that we had before. We're going to make all of them the same. Let's say we make this. So you can see it's a wind box basically type of structure. Alright, and let's say we're going to have a force Vy equal to 10,000 pounds applied over here. So each boom area that will be, so each one of these areas here, those will be the B's. So it says will be, we'll start from here, 1, 2, 3, 4, 5, 6. So each one of those areas here, B sub I is equal to 5 inches square. Okay, and you see that maybe I should call that one B sub R like on the equations of r equal 1 through 6. Okay, so the material for the torsion, we need to know that the modulus of elasticity for torsion is 4×10⁶ psi. So this is basically aluminum. And let's say that the thickness of all those different thicknesses is the same. So let's say T would be equal to 0.1 inch. All right. And now what we need is the dimensions. So basically this will be, let's say, inches dimension. So this is 10, 10, 10. And basically that's all we need. Okay, so in this case, we'll just see the effect of this shear force. Okay? All right, so following the procedure, what was step 1? It's basically to make cuts. Okay, so we have our two cell structures over here. Alright, so we need to make a cut on each cell so we can start the calculations there. So this will be, let's see now the number again, 1, 2, 3, 4, 5, and 6. Okay, we still have the booms over here. Okay, so if you want, here what we do is Q12. We make the cut so it's 0, it's open, and Q16 really will be Q61, but doesn't matter, it will be equal to 0. Okay, so now step 2. We need to look at the equation we had before, so we need to do shear flows. So do we have in these problems, we only have Vy, so if you want to put, we only look at Vy here on this structure, we could put Vy over here. Okay. So in these problems, what do we have on this long equation that we had initially? Alright, so now we go back to this long equation. So what do we have? We have Vx is equal to 0, Ixy is equal to 0 because we have a symmetric cross section. All right. So that the shear flow equation Q sub S reduces to what? So we'll have Q sub S will just be equal to negative Vy divided by Ixx times the interval 0 to S Ty ds summations of the booms b sub r times y sub r. Okay. So over here, sometimes you need to be careful, and this is the reason. This is the panel. So basically in all these problems here, we did not put it, but it's not that this is a stiffer, all these ones have here panel, okay? There's a panel or web on top over here, okay? And here and here and so on. So this is if the skin, if the panels, the webs are going to be active, this is this term. So this is panels, webs. And this is the effect of booms areas that basically takes into effect the flanges and the stiffeners. Okay, so here be careful, because sometimes in the problems they're going to tell you to assume that all the load, which is Vy, will be only carried by the, let's say, flanges and stiffeners. In that case, you will say that this term is 0. And sometimes it will tell you that to do the calculation, assuming that also the webs or the panels will carry some of the external load or some of the shear. So in that case, you also need to include this term into the calculation. And actually, this will also affect a little bit this one sometimes, okay? But just be careful about this. This will be the main difference. Here, since this is the first example, we're going to assume that these structures will carry on the external load using the beams and flanges, meaning that we'll take this term to be equal to 0, okay? So assuming that the skin does not carry any loading. I mean, any loading means any of the Vy. They're definitely going to have some shear, but so you will say T equal to 0. The equation becomes, so we only have Q sub S equal to minus Vy over I XX summation from R equal to 1 to infinity of B sub R Y sub R. All right. Okay, so over here, let me specify what would be the Y sub R. So we take our structure, okay, so we have 1, 2, 3, 4, 5, and 6. Alright, so the Y sub R is the distance from the neutral axis. So where is the neutral axis? The neutral axis is basically the line going through the centroid, from which the extension will be bending, okay? Alright, so the Y will be basically in that direction here. So if all the distance here is is 10 inches, what will you have? You will have y sub 1, y sub 2, y sub 6 will be equal to what? 5. And y sub 3, 4, and 5 would be equal to minus 5. Alright? And this will be B1, B2, B3, B4, B5, B6. Okay. And so we know now the y. So if you want, we can even write it down here very quick. So if you want, from figure, we have y1 equal y2 equal y5 will be equal to 5 inches, y3 equal y4, oops, this is 6, y5 equal y5 equal to minus 5 inches. And here all the b's, I didn't put it, but all the b's of r's were equal to 5 inch square. Okay, so in order to calculate, the only one we need is to find the IXX. So the IXX is equal by definition to y squared dA. So this is approximately equal, but this is because the effect of the skin is 0. It will be equal to the 1 to 6, because it's 6 booms, of y squared b sub r. Okay, b sub r is the area, so y squared dA br the square. So this would be equal to what? So we know we have 6. So there's 6 of them. Then if you want, what would be all the time the distance would be either plus or minus 5. So if you want, the effect of this one will be b1 times, so 5 times 5 squared, okay? Same thing for the top ones. And now what is the area is 5. So it's basically the IXX, which means the resistance of the bending in this direction. Alright? And if you do this calculation, from here we're going to get that IXX is equal to 750 inch square. Inch to the 4th, sorry. Alright. So now we can do step 3, which is calculate the Q sub S. So if we go back to this figure, what would be Q12? Q12 is 0. So we start from the cut, so you're going to know that Q12 is 0, so now we can do a calculation at Q23, so it will be equal to what? We use the above equation, we have it would be equal to Q12, okay, plus whatever happens on the next one, that would be Q23, but here's a minus sign, minus Vy over Ixx, and now this will be the effect of what? We went from here to here, now we go from here to here, okay, so from B2 y sub 2. So this will give you Q12 is 0, minus By is 10,000, Ix is 750, B2 is 5, and the Y2, since it's on top, is 5. Alright, and this will give you that Q23 is equal to negative 333.3 lb per inches. Okay, so now we do the same thing. What will you have? Q34 will be equal to what? Q23 minus by over Ixx. Before we had b2, now we're going to have b3 y sub 3. Okay, so this will give you what? Negative 333.3 minus 10,000 divided by 750. But this time what is b? It's also 5. But that be y sub 3 will be minus 5. Okay, so this, if you do the calculation, will give you that Q34 is equal to 0. Alright, so we did here 1, 2, 2, 3, 3, 4. Okay, I like, now let's go to, let's do maybe 1, 4, okay? So that one, yeah, let's do Q1, 4. Then you go to the next page. I might want to do a little figure. So that should be page 22. Okay. So if I do a quick little figure here, remember we have a cut here, we have another cut over here. We have 1, 2, 3, 4, 5, 6. And we did say that Q here 1, 2, due to the cut is 0 and Q16 is equal to 0. Alright. So now here Q14 basically will be equal. So remember we go around, but this will have here and also one from here, so it will be equal to Q12. Alright, if we start from here, plus Q16, that is also 0. Alright, so two of both will be going in. And now we go from 1 to 4 minus Vy over Ixx B1 y sub 1. So we start from here. These two flows, if you want, goes into this one, but they're both 0. Okay? And then you calculate from here to here. You could do from here, but then you need to wait to calculate this one. And I'd rather do first do all the calculation for cell 1, and then this will be cell 2. Okay? So in this case, we know this is 0. This is 0. So basically, you are left over here with minus 10,000 divided by 750. Now By is 5, and y sub 1 is 5. So this will give you again the Q14 equal to minus 333.3 lb inches. Okay, so now let's say we start from cell 2, so we're going to look at Q45. Now what would be Q45? We do the same thing. We'll have Q34 plus Q14. Okay, this one plus Q45, that would be minus By over Ixx before Y sub 4. So we know Q34 we calculated before to be equal to 0. So this will be equal to Q14, so minus 3.3 minus 10,000 divided by 750, that's 5. And now what should be Y sub 4 is minus 5. So if you look at it, it's basically the same thing that we had before over here. So that means that Q45 will be equal to 0. And then finally, we're going to have that Q. So now we go Q56 will be equal to Q45 minus Vy over Ixx of B5 Y5. If you want a little trick, the areas you need to put is the first number over here. So this will give you what? 0 minus 10,000 over 750. B5 is all 5, and Y5 was at the bottom, so it should be minus 5. So we have this negative with this negative, will give you that Q56 will be equal to 333.333 lb per inch. Okay, now this one, you don't really have to do it, but if you want to do it to check, so let me put here to check. You could do Q61, that would be equal to Q16, which we know is equal to what? 0, no? But let's see what the math will give you. We know this should be equal to what? Q56 minus By over Ixx. We go from here to here, so B6, Y6, so this gives you what? 333.3 minus the 10,000 divided by 750 times 5. Times 5 will be on top. So it will be 5 instead of 5 minus 5. So you can see that very quick. Q16 is equal to 0. Okay, so let us go back to the problem here and let's see if that makes sense. Let me just do this figure. Remember that all these classes about structures are based on summation of forces equal to 0 and summation of moments equal to 0. So if the force on the x direction, the two top ones, are 0, what should be the other two forces on the x direction? They should also be 0. Now, if this one is going, let's say 333 going down, this one should go 333 going up, so that you can have summation of forces on the y direction equal to 0 as well. Okay, so we did all those calculations, but with a little understanding you can go check in your work. Okay, so if this is 0, 0, this one should be 0 and 0. Okay, and now these 3 should count to 0. All right. So that was step 1, 2, 3. Now we need to assume the the same shear on each one of the cells. Okay. Alright, so before going to the next step, since I have the space, let's do the figure of summary. So we have okay, and the numbers were 1, 2, 3, 4, 5, 6. Okay, so let's see what we have. We have Q12 is equal to 0. We know this one is 0, but we know it's not direction, so Q12 equal to 0. Then we calculate Q23 was negative, so we know Q23 will be going in that direction, really. Okay, then this one Q34 is 0, Q45 is 0, Q16 equal Q61 is 0. And then what we had, Q14 is minus, already goes up. So Q14 here, let me say Q14. I'm not going to put the value, but basically it's minus 33.33, and then Q56, this one is positive, so this one is going up. Q56 equal to 333.33. Okay, so you see that there's an unbalance here of the forces on the y, on the x at 0. So basically you need to have some moments here that will make this structure not to twist. All right, so that's what we're doing. So that's a step. Let me see the procedure. Step 3. Okay. All right. So step 3 is basically assume that the twist of each one of the cells is the same. Okay, so this is step 3. Alright, so we say that each cell must have the same angle of twist. All right, so this is the condition, and we know that d theta dz is equal to 1 over 2a of u go around the cell of q over gt ds. Okay, so let us do the first one over here. Alright, the first time you need to be a bit careful, so you need this figure as well, okay, with you. So let's do for the first cell, let's say it will be this one over here, cell 1, cell 2. So we go through Q12, Q23, Q34, Q41. All right, that's the first cell. So let's say d theta dz for the first cell is equal to 1. It's 1 over 2a, which will be 1 over 2 of the area of the first cell. That would be pretty easy to find, which they will cancel out. Okay, because in this case they are the same, but it would be 10 by 10, and this one is also 10 by 10. So then when we equate these two equations, over here they will cancel out. Alright, so 2a1, and then we know the material is constant, is G, and that T is the same for all of them. So the thickness of these flanges, stiffeners is the same everywhere. So that simplifies a bit the calculations. Equal to 1 over GT. So this one you will see will cancel out. So now here, we need to do the QDS. So we need to go around the cell. So around the cell, what do we say we have? We have Q12 plus Q23 plus Q34. So Q12 plus Q23 plus Q34 alright, so we'll 1, 2, 2, 3. Okay, really should be minus Q23. Alright, because I'm already changing the sign. So, I mean, if we do it this way, if we take these values here, because we already put the sign, we can just put positive everywhere, okay? So it would be Q12, Q23, Q34 plus Q41, if you want. That is Q14. So basically we know this is Q14. Alright, and now we need to do the DS. So this is the Q. Now we need to do the DS. So the DS, we know that distance 1 to 2 is 10, 2 to 3 is 10, 3 to 4 is 10, and 4 to 1 is 4. Okay, but you can have different lengths over here, so you need to be careful. This can be different for each one Q, okay? Each Q might have a different S, but that's not the case over here. All the different S's here would be equal to, so S over here, I'm going to say, each one of the sides would be equal to 10. Alright, so now if I go and substitute here, you're going to get that this is equal to, let's compact a little bit the notation, 1 over 2A1 GT. Okay, here I forgot to do something very important on the figure, so that's what gave me here the mistake a little bit, so be careful over here. Alright, so let's go back for a second, and here we need to assume, let's see if I know the figure, that it will be a Q sub 1 going this way, and a Q sub 2 going this way. So really this shear flow here will be what? Q12 plus Q1, alright? This one will be Q23 plus Q1, Q34 plus Q1, alright? And this one will be Q14 times Q1 minus Q2. So let me write it down slowly so we can make sure. So, alright, so we have this here. So basically, all right. Right, let me change here the notation very quick so that I can make it more clear. And then I will add it at the end, okay? Right, so let's do it and then I'll do another figure so that you can understand. So this will be equal to so the first one will give you what? Q12, that's the one I'm calling now Q1 bar. So you want, maybe we can do it here. Q bar 12 will be equal to Q12 plus Q1. Q bar 23 will be equal to Q23 plus Q1. Q3 bar 34 will be equal to Q34 plus Q1. Then we need to be careful. This one here will be Q14 or Q41 will be equal to Q41 or Q14. So then will be plus Q1 minus Q2. Q45 is equal to Q45 plus Q2. Q56 equal Q56 plus Q2. And finally Q bar 61 or 16 will be equal to Q61 plus Q2. That might be, so the only thing we need to do here is we can leave it that way. Alright, so now when we come over here, this one will give you what? This is Q bar 12 was Q12 that is equal to 0, so this will give you just Q1 because it's Q12, okay? Q bar 12 equal Q12 plus Q1, okay? Q12 is 0. Now plus, what is Q23? Q23 is minus 333.3 plus Q1, okay? So this is Q12, and this is Q23 plus Q34 here we know is 0, so it will be just Q1 plus Q1, so this is Q34 plus, now we need to be careful with this one because what will you have? You will have so let's see if you can see the figure. So for this one, what we'll have? We'll have Q14 was equal to what? Okay, so we made it up, so it's going up, so this will be positive, so it will be 333.3. Then we'll have what? Plus Q1, that is going in the same direction. And then we'll have Q2 will be going opposite direction, minus Q2 due to the angle of twist. Okay, and really all this should be multiplied by 10. Okay, by the S over here. So let me just put the S over here. It will be equal to S. All right, divided by everything. And this will be here, Q41 or Q14, okay? All right, so after we do the calculations, what we're gonna get over here is that d theta dz for the first cell will be equal to, let's say, S over 2A1 GT factor of what? So let's see how many Q sub 1 we have. 1, 2, 3, 4. So 4 Q sub 1. This 333.3 cancel with this one. So we have, and then minus Q sub 2. Alright, so this will be our first, this will be the angle of twist for cell 1. Alright, so this is cell 1. Angle of twist. Alright, now we need to do the same thing for the second one. So we have d theta dc of the second cell will be equal, I want to go a little bit faster here, would be 1 over 2A2 GT, okay, of what? So we end up using the same notation, will be 4, 5, 5, 6, 6, 1, and then 1, 4. So we have Q45 plus Q56 plus Q61 plus Q bar 14, and all these times S. So this will simplify to what? 2S over 2A2 GT. Okay, so what is Q45? Is 333, so we have 33.3 plus the Q2. So that means we'll have it here Q2 plus 333.3. Now Q56. Oops, sorry. One little mistake. So let's say this will be, no mistake, but Q56 is 0 plus Q2. So let's say this time here will be Q bar 45. And now the next one will be 333.3 plus Q2. So this will be Q56. Okay. Now Q61 is 0, so this will be just equal to plus Q2. So this is Q61. And now we need to be careful here because we go to Q14, this will be equal to what? Will be equal to positive Q2 minus Q1, so it will be plus Q2 minus Q1, and now this one go on the opposite direction, so minus 33.3. Okay, if you think about it, this is just like in electrical classes when you do all the currents going into one node. Okay, so it's kind of similar. All right, and we have this, and all this term over here would be Q14. All right, so this equation here would simplify to what? D theta dz of the second cell equal to S over 2A2 gt of what? We're gonna have 1, 2, 3, 4, so 4 Q sub 2 as before. The 333 will cancel with the 333.3, so minus Q1. All right, and this will be cell 2 angle of twist. Okay, so now what we need to do is just equate these two equations because that's the condition on top. All right, the condition we had at the beginning for step 3. So 24, so we'd say equating d theta dc of the first cell with the angle of twist of the second cell. What do we get? So we get 1 or S over 2A1 gt of 4 Q sub 1 minus Q sub 2 equal to S over 2 A2 gt of 4 Q sub 2 minus Q sub 1. Okay, so in this case you see that all these terms here will cancel out, but that's not always the case. Okay, the equation might just be a little bit more cumbersome, not complicated, but cumbersome, yes. So this is going to simplify to what? 4Q1 minus Q2 equal to 4Q2 minus Q1. So basically this equation, will give you what? Basically will give you 5Q1 will be equal to 5Q2, which basically will just tell you that in this case, and it's because obviously everything is symmetric, that Q1 will be equal to Q2, but if you want it to be mathematical, this would mean that Q1 minus Q2 will be equal to 0. So let's say this will be our first equation. We have one equation, two unknowns, okay? So we need to find another equation in order to be able to solve for Q1 and Q2. All right, so this is where now we need to do, I think it's step 4, where you're going to equate basically you say the external moments to the summation of the internal, that would be basically the shear forces. All right, so when we take the moments, we always need to specify about which point. All right, so let's do the figure over here. All right, so what is the figure? Oh, let's just redo it here very quick. I mean, I could just put the force here, but all right. Okay, and here we have the boom areas. Basically, these boom areas, what they represent is the area of all this stuff. Okay, so we know this is 1, 2, 3, 4, 5, 6. Now we have here Q12, Q23, let's do the bars, maybe a little bit easier. Q34, Q45, Q56. I'm just going to do all the them in the same direction, Q61, and let's say here we have Q14. Okay? That this one already includes the 1 and 2, so this would be cell 1 and cell 2. Okay? And we know might be too much of the same figure, so maybe let me do another small figure here. Alright, we have 1, 2, 3, 4, 5, 6. And this one for the dimensions, we know this is 10, 10, 10, 10, 10, 10, and 10. Okay? Just to make it easy. Alright. So over here we need to take the moments about a point. So it doesn't matter which one, but let's take either 1 or 4. Let's say 4. Okay? So I will say here is what? Summation of moments due to the external forces about point 4 will be equal to the moments due to the shear, which is all those. So basically the external will be here the Vy just right here. Okay, so the moment created by Vy about 0.4 should be equal, should be counter-reacted by all those shear forces, okay, going around. So be equal to the summation of moments. I say internal, but it should be shear forces also acting about 0.4. And let's over here we always go counterclockwise positive. Okay, you need to select the direction. So we do this. All right, so let's see what will be the moment of the external force. First, will it make about 0.4? Will it be positive or negative? So it will be positive over here because it will be the value of the force is 10,000. What is the value of the arm? Will be 10. All right. Now, let's say let's start by Q12. So I'll be the moment created about 0.4. This will be Q12. Then we can care about the value Q12 times 10. So shear flow is force per unit length. So this will be the force here now times the arm will be is also 10. Okay. Plus Q23. Wait, I assume was positive. Yeah, also will be positive Q23 times 10, the value of the force. The arm will also be 10. Now we go to, so Q12, Q23. Let's go to, so now 3, 4, 4, 5 will not be a moment because it goes through 0.4, and Q4 either, so we have Q56. Q56 will also be positive, plus Q56 times 10 times 10 plus Q61 times 10 times 10. So this is basically, as we said before, this is the force, and this 10 here would be the arm of the moment, okay? All right, so if I simplify this equation a little bit because it's all 10, 10, 10, 10. So 25. So this will mean, okay, since we go to the next page, really we have 10,000 times 10 on the left hand side, and then on the right hand side we can have that this will be equal to 100 times Q12 plus Q bar 23 plus Q bar 56 plus Q bar 61. All right, so this you can see that you can eliminate this 100, let's say, with 2 zeros over here. So this will give us what? 1000 on the left hand side. And now this should be equal to what? So we can say that Q12 is equal to what? So as before, Q12 is only equal to Q1. Q23 will be minus 333 plus Q1. And which one do we need? Okay, and you can go this way. Q34 would be, is not needed. Q41 is not needed. Q56 would be 333.3 plus Q2, and Q61 would be Q2, okay? So if we substitute all this stuff over here, let's say, what will you have? You will have, and we just say over here, this Q12 will be equal to Q1. All right. Now the Q23 will be equal to minus, let's see, what do we have before? Q23 will equal, yeah, to minus 333.3 plus Q1. Okay, Q56 was equal to plus 333.3 plus Q2. Okay, I'm copying all this stuff from this page over here, okay? So Q56 is just equal to this. And then Q61 is plus Q2. All right. Okay, so this term is really Q12. This term here is Q23. This term here is Q56. And this one is Q61. Okay. All right, so now we've simplified this equation. What do we get? We're gonna get 1000 is equal to what? So we see the 333 will cancel out. We have Q1, so 2Q1 and 2Q2. So we have 2 Q1 plus 2 Q2. So we can say right away that this will give us a second equation saying that Q1 plus Q2 equal to 500. And this will be our second equation. So let's see, how did I call this before? Sorry, so I'm looking for page 24. Here we go. So it will be equation 2. So now solving one and 2, which basically, what was it? We had Q1 minus Q2 equal to 0, and we have Q1 plus Q2 equal to 500. So that's very easy to solve, okay? So right away, from here, you're gonna get that since you know Q1 equal Q2, you're gonna have Q1 equal Q2 equal to 250 lb inch. All right. So now, finally, we can see what will happen with every one of the stresses. So Q12 we say was equal to what? Was Q12 plus Q1, but we know Q12 was equal to 0. So this will mean what? That Q12 is equal to 250 lb per inches. Now Q23 will be equal to what? Q23 plus Q1. Q23 was equal to what? So again, you can go to the other pages. So Q23 is equal to minus 333.3, okay, plus 250 will give you minus 83.3 lb per inches. Q bar 34, doing the same thing, will give you Q34 plus Q1. So I think Q34 here was 0, no? So it will give you again 250 lb per inch. Now Q, if you do the first cell, so Q, let's see what we have this page. We can go with this one here. It'll be a little bit easier. Now Q here we say Q41 or Q14 was equal to what? Q14 plus Q1 minus Q2, okay? So we know these two are equal. So this one would cancel with this one. And Q14, that gives us equal to then to the Q14, I think was 333. Let's check because let me go and check over here. So Q14, okay, it was going up, so it actually needs to go down, so it should be negative. And was equal to negative 3333. Okay, so basically it's negative 33.3 lb per inch. Okay, and Is that it? We have some more. Q. So the bottom would be 45. Would be Q45 plus Q2. Q45 is 0. So this means Q45 will be equal to 250 lb per inch. Now Q56 would be Q56 plus Q2. So this will give you the 333.3 plus 250 will give you the 583.3 lb per inch. And finally, I'm going to do it right here. Q61 is equal to Q16 plus Q2. We know this is 0. So this means this would be 250 lb per inch. Alright, so maybe I can underline these values. Okay, so finally what it's nice to do, you just do a last little figure summarizing all the results. So now what I like to do is just one quick figure in which we'll have all the stresses, all the shear flows. This way, so that we have 1, 2, 3, 4, 5, and 6. And here you can say this will be here 250. This one go up 83.3. This one go up here 33.3 because it was negative, so it goes up the direction. This one here is 250. 250 again. I'm going to do the top again because I know it's going to be opposite direction, 250. And now this one will be up 583.3. Okay, so this is the shear flows distribution. Okay, and now just last, I just want to show you that in order to do all these calculations, okay, I have a MATLAB file over here, all right, where basically you see the boom areas all the same. This will be the distances are all the same. This is the areas. So this would work for even different areas, different and so on. So I'll calculate the moment of inertia. This will be assuming that the panels, the skin does not affect, otherwise the IX will be different, okay? Shear force, then I do the Q12 with all the expressions. All right, then I guess this is, you see the Q bar 12, this will be the unknown for the shear flows on each cell, so that the twist will be the same. Angle of twist, these are the two equations. So that's what I do. So this is equation 1, all right? Then this one, what I do is that, I think now you can do it with symbolic with MATLAB, but what I did this one is, I take this equation over here, okay? So that gives me the equation number 2. I go to Maple and say solve, and basically you see for different thicknesses, it gives a long expression, but again, this is for, you know, all those T's can be different, and Q2 will be different. You don't have to do it this way. and then at the end the total distribution. So if I run this, so that's basically what I did. You see all the values here showing up, okay? Which is the one I used for the equations. And okay, so that would be it. Thank you for your attention. And let me close this.